do as well. And you could have some friends, or if you have kids around, you can even play the CSI game with this. So the idea of using DNA evidence is based on the concept that all humans have similar DNA, but all humans also have different DNA. We all have 5 fingers and 5 toes and eyes and hair and stuff like that, so some of our DNA is identical. But we can tell differences between people by the differences in their DNA. So ideally, what we would do is isolate DNA from a crime scene and then just figure out the whole sequence, all those, the sequence of those 4 letters for a person. The problem is the DNA sequence is 3 times 10 to the 10th, which is 30 billion letters. And so to figure out what the order is for that much is just a ridiculous amount of work. So what's typically done is we do what are called restriction fragment length polymorphisms, and what that's called RIFLIP analysis. And first of all, I want you to understand DNA evidence isn't really that complicated, but the general population doesn't understand it. Kind of like what happened with fingerprints in the 1800s. Fingerprint evidence is very compelling. Everyone understands that now, but in the 1800s, people didn't get it. So the idea is this: you take the piece, you isolate DNA from the crime scene, from the suspects, and we made up a whole story here of actually something that actually happened. And then there are enzymes that are isolated from bacteria that are called restriction endonucleases. And you take the DNA, you might put it into a few different test tubes, and then you incubate it with these enzymes. And what the enzymes do is they look at the whole sequence and they cut it at certain sequences. So for example, there's an enzyme that will cut it every time it sees the sequence AATT, and it will cut it into AA, cut it between the AA and the TT. Another one might cut it here, or between the C and the G. Another one might cut it here. And so the idea is, if you look on this is in the lab manual, if we look at just this first sequence and we say, okay, let's cut it every time there's an AATT, so that's the red lines here. So this is 85 letters long, but if I cut it with AATT, I'd get a 27, a 22, and a 36, all right? Now, the chances that any 2 people would have the same sequence if we cut it this way, it actually could happen. I mean, all humans have similar DNA, and so there are going to be similarities. At the same time, all humans are different, and so there's going to be differences. The chances of 2 random people having the same sequence cut with one enzyme, it's going to vary. But let's say, for the sake of argument, that 10% of the population randomly would have the same size pieces if I cut it with AA and TT, all right? But then if I do it again, so I have one test tube I cut with AATT. Then I take another test tube and I cut it with the CCGG one, which is in this multicolored one. That's these lines here. If I cut it with CCGG, I'm going to get an 11, a 45, a 25, and a 4. Right? Now, again, let's say that 10% of the population will have exactly the same pattern with this. All right? But what are the chances that 2 random people would have the same with this and the same with this? Well, that would be 10% of 10%, which is 1%. Now, if you do that with 2 more enzymes, and let's say each is 10%, then it's 10% of 10% of 10% of 10%. All of a sudden, it's 10 to the minus 4th. And, and again, if you figure that they're not really 10%, they're lower than that, it starts becoming very, very compelling. Now, how do we know how big the pieces are? So what we do is there's a technique called gel electrophoresis, and what you do is, that's diagrammed up here. Right? You take the DNA after you've cut it. So I've got a test tube that's got DNA cut with AATT, and another test tube that's got DNA cut with CCGG, and another one that's cut with another one. And then maybe a set of standards that we know have pieces that we know how long they are. And then we put them in, literally you take kind of like Jello, and you put it between 2 metal plates, or just you pour a slab and you stick a comb in it, and you get a pattern that looks like this. And you pull it out when it's Jello, and you've got these wells, right, little spots. And then you can put the DNA in there, and then you attach it to a battery or a power source. DNA is negatively charged, and so the DNA will move towards the positive charge. The way this works is that smaller pieces will travel further. And so the DNA, which is all in one spot, will separate, and then you can put this in a stain, and you'll get lines on the gel that'll show up kind of like this pattern here. And if we run a sample that we know what the pieces are, we can say, okay, well, this piece was 22, and this is 27, and this is 36. And you see how we get different patterns for the AATT and the CCGG. All right? So that's basically how it's done. You take the DNA, you put it into X number of test tubes for each one you're going to do, you run them on a gel, and then you find out what the sizes of the pieces are. So what you're going to do, so for example, on this one, right, if I took the DNA from here, right, AATT, and I ran it on a gel, I would get this pattern. I'd have a 22, a 27, and a 36. Then in a separate well, I run the CCGG, and I'd say, oh, look, I can get what the sizes are. So what you're going to do here, we have DNA from the crime scene, and then we have 4 suspects. You're going to take it and draw lines for the AATT, for the CCGG, for the CAAC, and the CTTG. What I would suggest you do if you want to make a game out of it is take this piece of paper, make 4 copies, and do one with each of the enzymes, and then see how long the pieces are. You can get creative. You could take a large piece of paper and put marks, go 1 through 85, and then literally draw lines on it. And then you can use that to see which suspect has the same pattern. Does any suspect have the same pattern in all 4 analyses? And whatever suspect has the same pattern in all 4 analyses should be the one whose DNA was at the crime scene. So that's a very short discussion. The lab manual goes into more detail about how it's done. That's a short discussion of how DNA evidence works. So this is the last lab. This one you could actually do at home. You can do the strawberry stuff at home. It's pretty cool. And that's it for this class, and I'll get the grades posted after this is due. It was nice meeting you for the first handful of weeks. It would have been nice to get to know you guys better. When we're back face-to-face, whenever that is, if you're still going to Mesa, pop by and say hi. And best of luck to you in your future. Keep in touch. Shoot me an email every now and again. Kind of cool like that. I like to hear from former students. Take good care of yourselves. Bye.